Published by http://www.IJERT.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Rotation capacity of plastic hinges and allowable degree of moment redistribution of ductile flexural members Beegam Fathima M.Tech student, Structural, Department of Civil Engineering YCET, Kollam, India Abstract. The thesis aims to study the plastic hinge region behavior of ductile concrete members with variations in mechanical properties, boundary conditions, and geometric properties. The particular areas of investigation will be reinforcement yielding location, plastic strain distribution, and curvature localization. Region.Proposed equations for plastic hinge length will be incorporated into a mechanics-based approach to predict rotational capacity of flexural members.he study will help practicing engineers and researchers simulate the performance of ductile concrete members in a computationally efficient manner. Keywords A tabs, ductile concrete, plastic hinge, rotation capacity, pushover analysis. Introduction. Plastic hinge refers to deformation of part of beam wherever plastic bending occur. For RC flexural members, plastic deformation is localized in the plastic hinge zone after yielding of members. Generally formed at the supports, point of maximum bending, under concentrated load. E.g. for a simply supported beam subjected to point load, plastic hinges will occur at the position of point load. For a steel, the stress-strain behavior ends at elastic limit of the body, then it will vary at different rate. After the achievement of elastic state, the rate of strain is much larger than that of change in stress. At a point, stress got zero increment while the strain keep on increasing, this stress is called yield stress. Further force cause no increase in stress but an increase in strain, this state is called plastic state. In structural elements like beam, at maximum deflection condition, this stage is achieved, i.e., the beginning of formation of plastic hinges. When the body become fully plastic, at point of application of load, it is said that it has infinite strain value. Strain is only resisted by a constant moment, which develops at plastic hinges, called plastic moment. The load at which this condition achieved is called collapse load. Structure deforms at a greater rate with constant resisting moment. Hinge means that having no capability to resist moment, so the plastic hinge behaves like a standard hinge permitting free rotation. The assessment of the plastic rotation of reinforced concrete members is an essential aspect to avoid structural brittle collapse. Rotation capacity of a joint in a structural member under constant moment depends on characteristics of the formation of plastic hinge. The value of plastic hinge length depends upon the load distribution and cross-section of beams. Moment redistribution refers to the behavior of statically indeterminate structures that are not completely plastic, but have some reserved plastic capacity. When one location first yields, further application of load to the structure causes redistribution of moment. When the load is applied to the beam, it has the property to resist it. When the beam is indeterminate, it forms sufficient number of hinges to make itself determinate. Further increment in load does not increase the moment at the point where plastic hinges are formed. The increased load increases the moment in the less stressed section of beam. The process of shift of application of moment in the beam is termed as moment redistribution in a beam. It is economical to allow redistribution of negative moments, it exploits the ductility of RC beams. Reduces the complexity of reinforcement detailing at beam column junction and accommodates more space for concrete pouring. Ductility is an important property of structural members that allows large deformation and deflection to occur under overload condition. It is an important design parameter, where intense confinement should be provided to increase the ductility of members. It provides warning of failure for statically determinate beams and allows moment redistribution to occur in statically indeterminate beam at overload. The ductility of member can be determined from moment curvature relation, where large deformations indicate better ductility. Ductility can be increased by increasing compression steel content, increasing compressive strength and increase in ultimate concrete strain. It can be reduced by increasing tension steel content, increase in steel yield strength and increase in axial load. 2 objectives: to study and optimize the plastic hinge region behavior of ductile concrete members to determine the ductility demand and maximum capacity of the structure with respect to percentage moment redistribution, to determine the ductility demand and maximum capacity of structure with respect to rotation capacity of hinges, to determine the relationship of percentage moment redistribution and rotation capacity of beam hinges on response of special moment resisting frame. IJERT 10 is 060184. www.IJERT.org 373. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.IJERT.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06. June 2021 3. Methodology Data Collection Literature Review Software Study Validation v. Analysis A. Equivalent Static Analysis. The natural period of building is calculated by the empirical expression prescribed in the code. The total design seismic base shear calculation and its distribution along the height are done as per IS 1893, Part I, 2002. The seismic weight is calculated using full dead load plus 25% of live load. Modeling Analysis Result and Discussion SL number 1 2 3 4 5 6 7 9 10 11 12 13 14 15 16 Table 1, Binding Details Component Model Story Height Beam Column Values G plus 8 3.2 m 250 x 500 mm 450 x 450 mm Wall Thickness Material Grade of Steel Slab Thickness Seismic Zone Importance Factor Type of Soil Type of Structure Response Reduction Factor Live Load Roof Load 200 mm M25 Fe 415 150 mm 3-1 Medium Concrete 5-3 kN/M2 1.5 kN/M24. Modeling The building is considered to be situated in Zone 3, Kerala. As per IS 456, building is considered as SMRF. ATABs implement the plastic hinge properties as FEMA 356 or ATC 40. Hinges are assigned once the structure is modeled. B. Pushover Analysis. First pushover analysis is done for gravity loads incrementally under load control. Later the subsequent lateral pushover load case is specified to start from final conditions of gravity pushover load case. Lateral load applied is obtained from ESA. Moment rotation values are assigned to all members by carrying out moment curvature analysis based on section properties and reinforcement details at the hinge location. For column moment rotation values are obtained for constant axial compressive load. The flexural M3 hinges are assigned for beam elements and PM2 M3 hinges are assigned for column elements. These values are generated based on material model for concrete and steel, by using equilibrium and compatibility equation for each element. Where M3 equals rotational hinge about major axis, M2 equals rotational hinge about minor axis and P equals compression hinge. Various parameters are used to study the plastic hinge region behavior of ductile flexural members. These parameters are varied by 50% from the actual and the plastic hinge region behavior were analyzed. Stiffness is increased and decreased by 50% from the actual and the behavior is analyzed. Fig 2, Moment Redistribution v/S Stiffness. Fig 1, 3D Model. Fig 3, Maximum Rotation Capacity v/S Stiffness. IJERT 10 is 060184 www.IJERT.org 374. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.IJERT.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 From the graph, moment increases when stiffness is varied 50% and rotation capacity is higher for beam with less stiffness. Fig 7, Hinge formation corresponds to shear area. Fig 4, Hinge formation corresponds to stiffness from the figure. Hinge formation is almost same when stiffness varied by 50%. B. Shear area is increased and decreased by 50% from the actual and the behavior is analyzed from the figure. When actual shear area of beam is varied 50%, number of hinges increases. C. Torsional modifier is increased and decreased by 50% from the actual and the plastic hinge region behavior is analyzed. Fig 5, Moment redistribution v/S shear area. Fig 8, Moment redistribution v/S varying torsional modifier. Fig 9, Maximum rotation capacity v/S torsional modifier. Fig 6, maximum rotation capacity v/s shear area from the graph. Moment redistribution increases very much when shear area is varied 50% and rotation capacity of hinge reduced very much when shear area varied 50% from the graph. Moment redistribution increases very much when torsional constant is varied 50% and rotation capacity of hinge reduced very much when torsional constant varied 50%. IJERT 10 is 060184 www.ijert.org 375. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig 10, hinge formation corresponds to torsional modifier from the figure. When torsional constant varied 50%, number of hinges increases slightly. Shear reinforcement is increased and decreased by 50% from the actual and the plastic hinge region behavior is analyzed. Fig 13, hinge formation corresponds to shear reinforcement from the figure. Less shear reinforcement leads to more plastic hinges because it might not satisfy minimum shear reinforcement criteria. Tension reinforcement is increased and decreased by 50% by actual and the behavior of plastic hinge region is analyzed. Fig 11, moment redistribution v/s shear reinforcement. Fig 14, moment redistribution v/s tension reinforcement. Fig 12, maximum rotation capacity v/s shear reinforcement from the graph. Very less percentage of shear reinforcement tends to more moment redistribution and rotation capacity. Fig 15, maximum rotation capacity v/s tension reinforcement from the graph. Moment redistribution decreases with increase in tension reinforcement and rotation capacity increases with increase in tension reinforcement. IJERT 10 is 060184 www.ijert.org 376. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig 16, hinge formation corresponds to tension reinforcement from the figure. For all percentage of tension reinforcement hinge formation is almost same. Boundary condition plastic hinge region behavior is analyzed by the beam is considered as simply supported and fixed. Fig 19, hinge formation corresponds to boundary condition from the figure. The damage probability is slightly higher for fixed beams than simply supported beam. Span to depth ratio is varied from the actual and thereby plastic hinge region behavior is analyzed. Fig 17, moment redistribution v/s boundary condition. Fig 20, moment redistribution v/s span to depth ratio. Fig 18, maximum rotation capacity v/s boundary condition from the graph. Moment redistribution is higher in case of simply supported beam and rotation capacity is less for simply supported beam. Fig 21, rotation capacity v/s span to depth ratio from the graph. Span to depth ratio is directly proportional to moment redistribution and inversely proportional to rotation capacity. IJERT 10 is 060184 www.ijert.org 377. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig 22, hinge formation corresponds span to depth ratio from the figure. When L/D ratio increases hinge formation also increases. Column size is varied from the actual and thereby plastic hinge region behavior is analyzed. Fig 25, hinge formation corresponds to column size from the figure. Hinge formation is highest for larger columns, due to larger column to beam linear stiffness ratio. Plotted moment redistribution and rotation capacity pushover curve by the values obtained from analysis on the various parameters for plastic hinge region behavior of ductile flexural members. Fig 23, moment redistribution v/s column size. Fig 26, moment redistribution pushover curve from the graph. lower percentage of moment redistribution in beam leads to more stronger structure. Higher percentage of moment redistribution in beam leads to more ductile and economic structure. As per CL 37.1.1 of IS 456:2000, the maximum moment redistribution should be within 30%. So optimum percentage of moment redistribution lies in between 25% to 30%. Fig 24, maximum rotation capacity V/S column size from the graph. Moment redistribution is less when stiffness ratio of beam and column becomes almost equal and rotation capacity depends on the distance from column to hinge location. Fig 27, rotation capacity pushover curve IJERT 10 is 060184 www.IJERT.org 378. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.IJERT.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. From the figure, rotation capacity around 100 kNm leads to more stronger section. Corresponding moment redistribution around 100 kNm rotation capacity is 25% to 37%. Based on the values obtained from moment redistribution and rotation capacity pushover curve, yield capacity of the structure is analyzed. Fig 28, yield capacity V/S moment redistribution. Fig 31, ultimate capacity V/S rotation capacity from the graph. Ultimate capacity should be higher to prevent necking of the members due to strains. Ultimate capacity is highest for moment redistribution 25% and rotation capacity 100 kNm. Relationship of moment redistribution and rotation capacity of beam hinges on response of special moment resisting frame is analyzed. Base shear. Fig 29, yield capacity V/S rotation capacity from the graph. Upper limit of force that can be applied without producing permanent deformation increases with decrease in moment redistribution. But lower percentage of moment redistribution leads to less ductile structure. Yield capacity is higher for structure with rotation capacity around 100 kNm. Based on the values obtained from moment redistribution and rotation capacity pushover curve, ultimate capacity of the structure is analyzed. Fig 31, moment redistribution V/S base shear. Fig 30, ultimate capacity V/S moment redistribution. Fig 32, rotation capacity V/S base shear from the graph. The ratio of moment redistribution to base shear is 0.0046. Base shear increases with increase in percent moment redistribution. The ratio of rotation capacity to base shear is 0.0011. Base shear decreases with increase in rotation capacity. IJERT 10 is 060184 www.IJERT.org 379. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.IJERT.org B.Story Shear International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. From the graph, the ratio of moment redistribution to inter-story drift is 0.0058. Drift increases with increase in percent moment redistribution. The ratio of rotation capacity to inter-story drift is 0.0025. Drift decreases with increase in rotation capacity. Story stiffness. Fig 33, moment redistribution V/S story shear. Fig 37, moment redistribution V/S story stiffness. Fig 34, rotation capacity V/S story shear from the graph. The ratio of moment redistribution to maximum story shear is 0.0197. Maximum story shear decreases with increase in percent moment redistribution. The ratio of rotation capacity to story shear is 0.0011. Maximum story shear decreases with increase in rotation capacity. Story drift. Fig 38, rotation capacity V/S story stiffness from the graph. The ratio of moment redistribution to maximum story stiffness is 0.009. Maximum story stiffness decreases with increase in percent moment redistribution. Ratio of rotation capacity maximum story stiffness is 0.0029. Maximum story stiffness increases with increase in rotation capacity. Fundamental time period. Fig 35, Moment redistribution v/s story drift Fig 39, moment redistribution v/s time period Fig 36, rotation capacity v/s story drift IJERT 10 is 060184 www.ijert.org 380. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig 39, rotation capacity v/s time period from the graph. The ratio of moment redistribution to time period is 0.0058. Time period increases with increase in percent moment redistribution. The ratio of rotation capacity to time period is 0.0023. Time period decreases with increase in rotation capacity. 6. Conclusion: while doing performance-based design, following points should consider to limit the moment redistribution within 30%. Shear area and torsional constant should not vary above 25%. Avoid simply supported beam as possible. Provide percentage tension reinforcement above 1.2. Span to depth ratio should be within 12 including modification factor. Rotation capacity of the hinges decrease with increase in stiffness, shear reinforcement, and span to depth ratio of the beam. Column size does not cause much rise in moment redistribution. Percentage moment redistribution is proportional to base shear, story drift, fundamental time period and ductility demand. Percentage moment redistribution is inversely proportional to story shear, story stiffness, yield capacity, and ultimate capacity. Rotation capacity is proportional to story stiffness and inversely proportional to base shear, story drift and fundamental time period. References: 1 R. Prabhakara, B. Nambiar, R. Rockall, 2020, Analysis of Rotation Capacity of RC Beams over Formation of Plastic Hinges, Advances in Structures, System, and Materials, 259-266. 2 John A. Reif, 2019, Plastic Hinges and Rotational Capacity of Ductile Flexural Members, Engineering Structures, Vol. 200. 3 Ling Li, Wenzhongzhen, Ying Wang, 2019, Review of Moment Redistribution in Statically Indeterminate RC Members, Engineering Structures Vol. 196. 4 Abdel Hafidnwala, 2018, Size Effect on the Plastic Rotational Capacity of RC Element, Critical Review of EC8, AJEC, Vol. 24, ISSUE 10. 5 M. V. Loj, M. P. Suresh Kumar, 2018, Plastic Hinge Zones of Reinforced Concrete Structures, ISSN 0076-5131, Vol. 5, Issue 10. 6 Fang Yuan, Yufei Wab, 2017, Effect of Load Cycling on Plastic Hinges in Nonlinear Behavior of RC Buildings, Engineering Structures, Vol. 124. 7 Krishnanan ITP, Jairesh CG, 2016, A Review on Moment Redistribution in Continuous Reinforced Concrete Beams, IJERT Vol. 3, Special Issue 23. 8 Enriz Lopez, Antonio Thomas, 2016, Influence of Adjusted Models of Plastic Hinges Behavior of RC Buildings, Engineering Structures, Vol. 124. 9 Ricardo N.F., D.O. Carmo and Sergio M.R., 2014, Ductility and Linear Analysis with Moment Redistribution in Reinforced High-Strength Concrete Beams, ASECH. 10 M.S. Mirfat, Farzania, 2014, Evaluation of Moment Redistribution Demand in Continuous Beam Under Gravity and Seismic Loads, WCEE China. 11 Ahmed Said Tawfiq, Ashraf El Zanali, 2014, Behavior and Ductility of High-Strength RC Frames, BBRC, Vol. 10. 12 Ayt Lone, Sumei Zhao, 2012, Analysis of Plastic Hinge Regions in RC Beams Under Monotonic Loading, Engineering Structures, VOL 34. 13 Muhammad Madala, Farouk KB, 2011, Evaluation of Ductility and Allowable Moment Redistribution in Reinforced Concrete Structures, Canadian Journal of Civil Engineering, 27, 6/1286-1299. 14 James John, Vinayak and M.S., 2011, Redistribution of Negative Moments in Beams Subjected to Lateral Load, JKCI, 23, 6. IJERT 10 is 060184 www.IJERT.org 381. This work is licensed under a Creative Commons Attribution 4.0 International License.